Namaskaram. Last session we have seen the inner product on a vector space. In this session we will define norm from an inner product. Okay, and norm is the generalization of the concept modulus. Okay, the definition of norm or magnitude. Let V be an inner product space, then norm denoted by like this using double vertical line. Okay, uh, for example, norm of U like this. Norm of a vector u belongs to V is defined by norm of u equal to square root of positive square root of inner product of u. We consider an inner product space V. We know that V is a inner product means V is a vector space together with a function like this, and this function has some properties. Okay, that is our inner product space. Then you can define norm using this inner product. How? You choose an arbitrary element. You choose any element from capital V, that will be u. Then we can define norm u. Sorry, can define norm u like this: positive square root of inner product of u, right? And what about the inner product of UU? By the definition of inner product, we know that inner product of UU is always non-negative, always greater than or equal to 0. Okay. Okay, so this inside term is always greater than or equal to 0. So what about the square root? This square root means positive square root. Okay, in standard, for example, we consider square root of 4. What is square root of 4? It is 2, not minus 2. Okay, square root of something means is a positive square root. That is universally accepted notion. So here it is a positive square root of inner product of UU, and the inside function inner product of UU is always non-negative. So this square root exists and it's a real number. Clear? And one more thing, we consider only positive square root. So this is greater than or equal to 0. So norm of u is always greater than or equal to 0. Clear? As mentioned in the introduction, norm u is the generalization of the concept modulus. And what is modulus? You consider a xy plane, choose a point z from xy plane, let it be xy. And what about the mod z? Mod z is the distance between the point and origin and denoted by mod z, right? And we know if x is equal to xy, then its modulus value is equal to square root of x square plus y square using Pythagoras theorem. Okay, and this norm is the generalization of modulus. Okay, so consider a problem. Find the Euclidean norm of this vector x is equal to 1, 2, 3. It's clear that this belongs to the inner product space R cube. We know that R cube is an inner product space with the Euclidean inner product. Okay, and we have to find the norm corresponding to this that inner product. That's why this is called a Euclidean norm. Okay, Euclidean norm is the norm corresponding to Euclidean inner product. Okay, so corresponding to every inner product, you can define a norm on that space. So what is our Euclidean inner product? Okay, by definition, this is our Euclidean inner product. Inner product between x and y is equal to x transpose y. You treat x as a x and y as a column vector. Okay. So what about norm x? By definition, this is equal to positive square root of inner product of xx. So first we have to find inner product of xx. By definition, this is equal to x transpose x. That's the definition of Euclidean inner product. Okay, and what is x transpose? The transpose of this column vector, that is 1, 2, 4 into x. 1, 2, 4. Okay, you can expand this one. This is equal to 1 square plus 2 square plus 4 square. Clear? And this is 16 plus 4, 20, 21, 20 plus 1, 21. Okay, so this is the inner product of xx. We have to find norm x. How to find? You simply take the positive square root of this one. So positive square root of 21. This is the norm of this vector. The interesting thing is this Euclidean norm is same as the our normal modulus in 3D and 2D. Okay, because in 3D you consider a point x, y, z. Then what is the distance between the point and origin? That is same as square root of x square plus y square plus z square. In this case, what about inner product of xx? That is same as, let it be, suppose this is xyz. Then this become x square plus y square plus z square. Then there is a positive square root that gives the same value. Okay, so actually the Euclidean norm is same as the usual modulus in 2D and 3D. Okay, but if you choose another inner product, then you can find another norm. So that is depending on the context. Okay, next we will discuss some properties of norm. The first property, norm u equal to 0 if and only if u equal to 0. Okay, the proof is very simple. You consider norm u equal to 0. Norm u equal to 0 means what? That is if and only if its square is also 0, right? Because norm u is a number. So norm u equal to 0 means its square also 0. Then what about norm u square? By definition, norm u is equal to positive square root of uu. So what about the square? Square is inner product of uu equal to 0, right? Then inner product has a property. Yes, this second property. Inner product of uu equal to 0 if and only if u equal to 0. Next we use this property. That is if and only if, oh sorry, u equal to 0. So we are starting from norm u equal to 0 and only if u equal to 0. That means whenever norm u equal to 0, that is possible only when the vector is 0. Okay, conversely the vector is 0, then its norm is 0. That is true in our usual calculus. For example, we consider R2 and a complex number or a number from the plane, that is Z. Suppose this distance, that is mod Z. Okay, mod Z equal to 0. Mod Z equal to 0 means what? This distance equal to 0. This distance equal to 0 means Z is 0. You got it? And conversely, if Z equal to 0, then the distance is 0. That's all. So this result says that this nice property is true for our generalized modulus function norm. Okay, next property. Norm of lambda u is equal to mod lambda into norm u. This is modulus of lambda. Okay, we assume that lambda is a real number. Then to prove this result, we consider norm lambda u square. We simply consider norm lambda u square. By definition, what is norm lambda u square? We know that norm lambda is equal to square root of inner product of lambda u lambda u. So this is square. So you can remove the square root. So this becomes inner product of lambda u lambda u. Using the property of inner product, you can take this lambda outside. So this will become lambda square into uu. Okay. Next we consider positive square root on both sides. That means we consider the positive square root of norm lambda u square. The right hand side is positive square root of lambda square into inner product of uu. And what about positive square root of inner product of lambda u square? And we know that this norm of lambda u is always greater than or equal to 0. That means we know that norm of lambda u is always greater than or equal to 0. You think about phi square. And what about the positive square root of phi square? This is equal to positive square root of 25. And we know that its positive square root is phi itself, because this phi is positive. Okay, so similarly here norm of lambda u is positive. So you take the square and take the positive square root, that gives the same norm of lambda u. Clear? And in right hand side, this become positive square root of lambda square into positive square root of inner product of uu. Right? And what about positive square root of inner product of uu? By definition, that is norm u. That's okay. The last portion is, what is positive square root of lambda square? Here our assumption lambda is a real number. Lambda may be 0, positive, negative. So what about positive square root of lambda square? That is equal to modulus of lambda. Why? For example, you consider minus 5 square and positive square root. Here, suppose here lambda is negative. Then what happens? This is equal to positive square root of 25. That is equal to 5. This is not equal to lambda. Here lambda is minus 5. So this is nothing. This is our modulus of lambda. Okay. So we know that this positive square root is always positive. So in general, positive square root of something square is equal to mod lambda. But in this case here the inside numerical quantity is positive, not negative. That's why mod lambda becomes same function. Okay, so this is equal to mod lambda. So norm of lambda u is equal to mod lambda into norm u. Okay, next we are going to define the concept of orthogonality in an arbitrary inner product space. So two vectors u and v belongs to V. Here V is an inner product space, are called orthogonal if inner product of uv equal to 0. And orthogonality means the concept of perpendicularity in our 2D or 3D. That is the concept of orthogonal. Okay, we know that two vectors are orthogonal in 2D or 3D means the angle between them is perpendicular. Okay, so this is the generalization of orthogonality in an arbitrary inner product space. If the inner product between u and v equal to 0, then you can say that they are orthogonal. Okay. Okay, another property. If u and v are orthogonal, then show that norm of u plus v square is equal to norm u square plus norm v square. Okay, this is the generalization of our Pythagoras theorem. For example, in 2D, let be this vector is u and this vector is v. Then we know that this distance is modulus of u and this distance is modulus of v. Okay, then this length is mod v. Then we know that this vector is nothing, this is u plus v. Okay, so this length is modulus of u plus v, right? So what about this is 90-degree. So what about the Pythagoras theorem? Pythagoras theorem says that this length square plus this length square is equal to this length square. Okay, so this is the generalization of that result. Okay, to prove this result, we consider the left hand side, that is norm of u plus v square. By definition, what is norm of u plus v square? That is equal to u plus v, u plus v. Okay. Next, you have to expand this inner product using distributive property of the inner product. First, we apply this third property. So this is equal to inner product of u comma u plus v plus u plus v. Next, you have to apply another property of the inner product, that is yes, this one. Inner product of u comma v plus w is equal to inner product of uv plus inner product of uw. That is uu plus uv, and this one become vu plus vv. Okay, and what about inner product of uu? We know that square root of inner product of uu equal to norm u, so this becomes norm u square. And what about inner product of uv? Our assumption u and v are orthogonal. Orthogonal means their inner product equal to 0, right? So this term is 0. Then what about inner product of vu? That is another property of inner product. We know the inner product of uv is same as inner product of vu, right? And this is equal to 0, so this is also 0. So this term is also 0. Then similar to this one, this is actually norm v square. So this is equal to norm u square plus norm v square. That's our result, and it's proved. Okay, next we consider another set, CAB. What is CAB? All real valued continuous functions on the interval AB. Okay, AB is suppose A is less than B. A is less than B. So set of all continuous functions, real valued functions on AB. For example, this function and this function. You think about all the functions defined in the interval AB. For example, f of x is equal to x square. It's a function, it's a well-defined function defined on interval AB. So this function belongs to this class. Okay, sin x. Yes, sin x is continuous in this interval. So sin x belongs to this class. Okay, exponential function, polynomial functions. Set of all continuous functions, real valued continuous functions on interval AB. That collection is denoted by CAB. Okay, and this set has a nice properties. First one is this is a vector space. The first property is this collection of functions. This collection contains infinitely many functions, and that collection is a vector space. We know that a set is said to be vector space only when it's satisfying set 10 conditions under these two operations, vector addition and scalar multiplication. So okay, so first we are going to define vector addition. Here CAB contains functions, for example f, g, h, like that, functions. Okay, real valued functions. So I'm going to define the sum of two functions. So what is f plus g? We know that a function is defined, or a function is defined by the action of the function on that variable. Here the variable is moving along the interval ab. Okay, so we have to define what is f plus f. How to define a function f plus g? By defining f plus g of x. Here we define f plus g of x using f of x and g of x, that is f of x plus g of x. Both are real numbers because f and g are real valued functions. So it is clear that the sum is also a real number. So f plus g of x is a real number. So it's a real valued function. It's a well defined function. Okay, so it is clear that f plus g also belongs to the same class. Okay, so this addition is closed. So first property is satisfied. Okay, and similarly we have to define our scalar multiplication. The scalar multiplication means we choose a arbitrary function from CAB and C is a scalar. Then what is CF? Again, CF is a function. So CF is defined by its action on x. So here we are going to define CF of x by C times f of x. F of x is non, because f is non, f of x is non. So this is C into, this is a normal product, C is a scalar. So it's a well defined. It is clear that f of x is a real number, C is also a real number. So this entire product is a real number. So it is so this CF of x is also a real number. So CF also belongs to same class. So this is closed under addition and closed under scalar multiplication. Then you have to verify rest of the eight conditions. Okay, if it is clear this CAB satisfies all the 10 conditions of vector space. Anyway, all of you please do this problem as a homework. Okay, you have to verify all the 10 conditions, all the remaining 8 conditions. Anyway, CAB is a vector space under these two operations. Okay, next we are going to show that this CAB is a inner product space. Okay, with the this is the definition of inner product. Inner product of fg equal to integral a to b f of x into g of x dx. Okay, and this is a very important space, the CAB, because this space contains functions. So this is important in if suppose we deal with the problem of signals, then maybe you can use this type of spaces. Okay, how to verify this inner product? You have to verify the conditions of inner product, that is we have to verify these 5 conditions. Okay, so first we consider inner product of ff. Okay, so we consider inner product of ff. By definition, what is this? Integral a to b f of x into f of x dx, that is f of x square. Okay, what is the geometrical interpretation of definite integral? Suppose this is our function f of x in the interval a b. Then what is the meaning of integral a to b f of x dx? Geometrically, this means area between the curve and x-axis. Okay, here instead of our function f of x, it is f of x square. Then what is the advantage of f of x square? This new function is always positive, always non-negative. So f of x square is something like that. Always its value is in positive side. Okay, so what about this area? Area is also greater than or equal to 0. So it is clear that this integral value is always greater than or equal to 0. So this function satisfies our first axiom. Okay, what about second property? Inner product of ff equal to 0 if and only if f equal to 0. Inner product of ff equal to 0 means, by first case we know that this is equal to integral a to b f of x square dx equal to 0. That is if and only if. Integral a to b f of x square equal to 0. That means what? The area between the function, this is our f of x square. Okay, it's a non-negative function. The area between this function f of x square, this Green's function is f of x square. So area between f of x square and x-axis is 0. Area is 0 means what about the curve? Curve is coincide with the x-axis. Clear? Otherwise, what happens? Suppose function is like this. Then there is a positive area. So this area equal to 0 means this function is coincide with x-axis. Function is coincide with x-axis means what is the value of the function? That is always equal to 0. That means f of x whole square is equal to 0. The square equal to 0 means what? Square equal to 0 means function equal to 0. So we are starting from inner product of f of equal to 0. Inner product of f of equal to 0 if and only if f of x is identically 0. F of x is identically 0 means that means our f, the function equal to 0. That is a 0 function. This is the 0 function in CAB. Okay, so that is means f equal to 0. Clear? So this function satisfies our second property. So you can easily verify the third property. You consider inner product of f plus g comma h, a distributive property. By definition, this is equal to f plus g of x into h of x dx. And again, this is equal to integral a to b. What is the definition of f plus g? That is f of x plus g of x into h of x. Next, you expand this bracket and split the integral. So this is like this: f of x into g of h of x and g of x into h of x. And by definition, what is this? This is inner product of fh, and this is inner product of gh. So this is the distributive property of this function. Third one is okay. And what about the fourth one? The fourth property, we consider inner product of lambda fg. By definition, integral a to b lambda f of x into g of x dx. And by definition, what is lambda f into lambda f of x? That is lambda times f of x. So this is equal to lambda into f of x. So lambda is a scalar you can take outside. So lambda into integral a to b f of x into g of x. This is equal to lambda into inner product of fg. So fourth one is okay. Last one is commutative. So we consider integral fg. This is the definition. They are real valued functions, so you can easily reverse the order. That means g of x into f of x dx. And by definition, this is equal to inner product of gf. So this function is commutative. So this function satisfies all the 5 axioms of the inner product. So CAB is an inner product space with this inner product. There are several inner products on CAB. Okay, anyway, CAB is an inner product space. And this is the standard inner product on CAB. Okay, check whether sin x and cos x are orthogonal in CAB. Okay, we consider the standard inner product. That means we have to check whether inner product between sin x and cos x is 0 or not. So with respect to our standard inner product, what is the inner product between sin x and cos x in this interval? That is minus pi to plus pi, the function sin x into cos x dx. Then what is 2 sin a cos b? Oh sorry, 2 sin a cos a, or we consider 2 sin x cos x. That is equal to sin 2x. So this become sin 2x by 2. Okay, then you can easily integrate the sin 2x, that is, yes, that is minus cos 2x by 2. Then substitute upper limit and lower limit. Anyway, this integral becomes 0. So it is clear that the function sin x and cos x are orthogonal in the inner product space C minus pi plus pi with respect to our standard inner product. Okay, that's it. Thank you.